All right, how are things going? Good. Questions?
So I did an ODP yesterday.
Mm-hmm.
Was that the one, like, I think it was ODP 10.
Yeah.
Do I have to do it again today?
No.
Okay.
So it's a 2-day program this time. So I forgot to post ODP 210 on Canvas yesterday morning, and somebody reminded me pretty late in the afternoon. So in case you were in the Monday, Wednesday section, you didn't notice that there was an ODP, right? I wanted to give people another day. So I posted it on Canvas, and then I extended the ODP to go an extra day. No, I think we're good for now. There's apparently not going to be a presentation today either because my camera is misbehaving. Yeah, I know. Let's just start this over. Oh, I got all kinds of hurt going on here.
Just zooming in on your video there.
Yeah?
And just repeat that over and over.
That would be cool. I could like move it around while you're trying to read it too. Make it really annoying. All right, other questions? I suspect my system is going to crash soon. All right, well, I want to talk about queues today. So we did stacks for 2 days. I want to talk about queues. Queues are first in, first out, as opposed to stacks, which are last in, first out. So it's a different ordering. The first thing that you put into a queue is the first thing that you're going to remove from the queue. Again, the model to keep in mind is kind of like a checkout line in a store or a teller line at a bank. First person who gets in that line will be the first person who's taken care of. The last person in line will be the last person taken care of. So you pull things out in the same order that you put them in. That's the whole concept of a queue. I don't want to go whiteboard again today. I might have to. And I've posted PA3 on Canvas. I'll talk about it tomorrow, but you can go ahead and look at it. And it's about stacks and queues. But the queue section may not make sense until we get through queue stuff first. So let me play with Windows for a minute. Say again? Yes, it is. It's because I got Chrome open.
Oh, that could be it. Chrome will do long range.
All right, we'll try this one more time, then we'll go whiteboard. Oh, I'm feeling good. There we go. All right, we're on the air. So queues. So here's a picture of a queue. And basically we insert on this end and we take out from that end. Okay, there's two ends to a queue and they're not the same. So we define the side where we insert as the tail, and the side we remove from is the head. So if we insert a 2, the 2 will go in first and come down here to that end, and then a 3 will go in, and then a 5, and a 7. Let's just insert prime numbers into our queue. And I haven't removed anything yet from the queue, so these are just queuing up, right? But if I were to remove whatever's at the head of the queue now, that's going to be the 2, and the queue is going to go away. That's convenient. How long has it been doing that? Okay, good. So if I remove from the head of the queue, the 2 is going to go away, and everything is going to kind of move forward in the queue. So now 3 is sitting at the head. And I can't move it on my page conveniently, but this is the new head of the queue. And if I say remove what's at the head again, it's going to remove the 3. And if I push some more things in the queue, I'm going to put in a 13 and a 17. And now I try to remove, I'm going to remove that third thing that was put in the queue, which is 5, and so on. So you got the basic idea, right? You go in one side and you come out the other side, and things stay in order inside the queue. That's the whole setup. So insert at the tail and remove from the head. That's just terminology, but that's pretty consistent in how people describe queues, and I'll stick to this convention in this course. So insert at the tail, remove from the head. And there's different ways to implement queues. We'll look at how to implement it with arrays. We'll look at how to implement it with stacks. Sorry, with linked lists. Okay, so those will be our 2 big options. So what are queues useful for? Anytime you want to manage things in order. Okay, a stack has this peculiar order that the last thing you put in is the first thing you bring out, right? And that's good for some things like returning from function calls, but it's bad for other things. So this is a first in, first out. So where would we want to do this kind of ordering? Well, for example, processing jobs on an operating system. So the CPU is mostly sitting idle. It's just kind of like talking to itself. And somebody tries to execute something, run a command, for example, and the CPU is going to say, okay, I'm going to run this person's program. And it'll run your program for a small section of time, like 10 milliseconds. And if somebody else has made a request to run a program, now it's going to take that second person's program and execute it for a little bit of time. And if there's a third program trying to run, it'll run that program for a little bit of time. And then it'll go back to the first program. So our queue might look like this. So here's process 1, here's process 2, here's process 3. So it's going to pull off what's at the head of the queue, which is process 1, execute that for a little bit of time. And then when the time expires, assuming process 1 hasn't finished, it puts it into the tail of the queue. And it looks at what job is sitting at the head, that's process 2, and it executes that for a bit of time. And suppose while process 2 is executing, process 4 comes alive and wants to execute on the CPU. Well, that goes into the tail of the queue. And now process 2 finishes its unit of time. It hasn't finished. It goes back into the queue, and our queue looks like this. So the next thing is going to be process 3, because that was waiting in the beginning, followed by process 1, but then process 4 will execute, because that came in after process 1 and before process 2. And if process 3 executes and it completes, it doesn't get put back into the queue. So we have this execution queue that is telling us what the processes are that are going to be executed and what order they're going to be executed in. And you can go into the operating system and find a data structure that's a queue that contains process IDs. And there's a queue for processes that are ready to execute. There's probably a queue for processes that are sleeping. There's a queue for processes that are I/O bound, and so on and so forth. Okay, so there might be multiple execution queues. And if you have multiple CPUs, you might have a queue for each one. And there's also queues with different priorities. So we could have a queue of jobs submitted by users that are waiting for execution, but we could have a separate queue of system functions that are given higher priority. And the operating system might say, okay, if there's any system level job that's ready to execute, I'm going to execute that next, regardless of how many jobs are in the user queue, because the system just gets higher priority. So that's one common use for queues in computers, is to store job information to control execution. This is called a round robin scheme usually. And it's one of those things where we can all be logged into the server and we can all be doing VI at the same time, and it looks like we have a dedicated machine, right? But in fact, the machine's only doing one thing at a time. If it's a single core machine, it's doing exactly one assembly language instruction at a time. And that instruction belongs to your job or my job or the operating system code or something. But you got 30 people logged into the server, you don't have 30 things happening at once actually. It's always one. If you got multiple cores, that changes. If you got multiple CPUs, that changes. But it gives the illusion of multitasking. It's kind of how people work too. All right, what else should you know about queues? If there's nothing in the queue, you can't remove anything from it, right? It's empty. And if you put 5 things in the queue and you remove 5 things, the queue is empty. A queue can get full depending on how it's implemented. So if we think of our queue as actually some pipeline that has a certain number of spots in it, it's possible that we keep adding things to the back of the queue, the tail, without ever removing anything from the head. And if this has a fixed size, eventually the queue is going to be full. And if we try to add one more thing to it, we're going to have to get an error because there's no space to add it. So it's kind of like a stack underflow and overflow, right? But it's really just being empty or being full. So what kinds of things would we like to do function-wise? We'd like some way to initialize a queue, which probably means creating space for it somehow and zeroing it out so that if we try to interact with the queue, we know that it's empty. We'd like an add or an insert function, which always works at the tail. We'd like a remove, which always removes from the head. We'd like an isEmpty. And maybe we'd like an isFull. When we implement this with a stack, we'll want an isFull. With a linked list, it's going to be kind of like the stack. Sorry, an array, not a stack. If we implement it with a linked list, it's going to be harder to tell that it's full.
I was just wondering, do you have like a specific number of spaces to put in the queue? You could kind of dynamically change.
So same as with a stack, right? We can implement this with an array. And if we run out of space, we could grow the array, right? Allocate a bigger array, copy things over. Or we can implement this with a linked list. PA3, you're going to do a linked list. So it's not going to have any predefined length. It's going to be limited by how much memory you can malloc. And the tests that I'll do on PA3 won't run out of memory, okay? Unless you're doing something crazy like making your node 1,000,000 bytes, right? Then it might run out of memory. But under normal use, you're not going to have to worry about things being full. But we do want to know if it's empty. And again, usually you're only removing things that you've added, but not necessarily, right? So in the case of an operating system that's processing jobs, one part of the system is stuffing things into the queue, another part of the system is removing things from there. Those two parts don't necessarily talk to each other. So it's perfectly valid to say, is there anything left in the queue? So we want an isEmpty function. Another example of a queue might be something like standard in or standard out. Right, these pipelines that we talked about in 224. What is standard in? It's the stream of characters typically that's being read by a program. It might be supplied from a keyboard, it might be supplied from a file, it might be supplied from standard out of another command that we connected with a pipe. But it's some sort of virtual pipeline that stuff is getting shoved into, and when we read from standard in, when we say fgetC, for example, we pull the first character out that was put into that pipeline. And if we say something like command 1, pipe into command 2, and we look at standard in on command 2, well, command 1 is executing, it's sending things to standard out. Those are ready to be consumed by command 2. But they've got to hang out somewhere until command 2 actually says, read a character, or read a line, or read a byte, right? They're basically hanging out in a queue. So this pipeline that we create between commands is effectively a queue. The first thing that goes into it will be the first thing that comes out. It would be really weird if it was a LIFO, because when you type, it would like read it backwards. Okay, so that's a common application of queues. When we talk about graph theory, we'll look at using queues to do traversal of trees or traversal of graphs. But we talked a little about depth-first algorithms. The other day, we were going through a forest, and we had branch points like this. And we said if we start going as far as we can until we dead end, then we back up and keep going. That's using a stack. A queue will do the opposite. A queue will start at some starting point, and it'll visit everything that's 1 hop away. And then it'll visit everything that's 2 hops away. And then it'll visit everything that's 3 hops away, and so on. And I don't know if I want to go through that algorithm right now. Maybe I'll come back to it. So let's talk about implementation. So we can implement a queue with an array. So again, we'll just deal with integers for simplicity. So I'm going to have an integer queue, and I'll make it a modest size queue, 10 integers. I'm going to write out all of our indices this time because we're going to use them all. So there's our 10 elements for storing information. And suppose I say add the element 5 to our queue. Well, we can put it anywhere we want. We don't have anything in our queue right now. But we want to have some sort of way of controlling where we insert things. So we're going to want a pointer that I'll call a tail, an index. And we're going to initialize tail to 0. And we're basically going to store at queue tail plus plus. So we're going to store the first element at the location given by tail, which is 0. and then we're going to increment tail to 1. So I'm going to do 5 adds to our queue. So when we say add 6, we'll store at the index given by tail, increment tail. Add 7 stores at index 2, increments tail. Add 8 stores at index 3, increments tail. Add 9 stores at index 4, increments tail. Now let's say we want to remove one element from the queue. And we're hoping that the remove is going to give us back our 5, because that was the first thing we added. So we need something that tells us where we should remove from. So we need a second pointer, which we can call head, which is also initialized to 0. So let me put that down here. So head equals 0. So when I say remove, head will tell me where to remove from in my queue. So I'll remove the 5, and then I want to increment my head. So at the next time I remove, I'm going to grab index 1, and the next time I'll grab index 2. So remove is going to say retrieve from queue head plus plus. So if I say remove again, I'm going to grab the element at index 1. That's a 6, and I'm going to increment my head pointer. And so I want to add a few more. So I'm going to add 5 more times. So add a 10, I'm going to store it at the tail index. That's a 10, increment the tail. Add an 11, I store it at index 6, increment the tail. Add 12, I store it at index 7, increment the tail. Add 13, I store it at index 8, increment the tail. Add 14, I store it at index 9, and I increment the tail. Suppose I try to add one more thing. If I try to store at the index given by the tail, that's going to be index 10. That doesn't exist. Potential seg fault. Is there any way I can store a 15 in this queue?
Well, you removed the 5 and 6, right?
I removed the 5 and the 6. So even though there's still a 5 and a 6 here, these aren't part of my queue right now. Right? Index 0 is available because I already removed that entry. So if I were to change my tail back to 0, I can keep going. So before we add this 15, after we add the 14, what does our queue look like? It looks like this. Right, and this is the tail. It was at 9, so let's go back to 9. And the head was at 2.
Before you change the tail to 0, don't you also want to check and make sure that the head is not 0?
Yes. So we need to do some housekeeping. So still before we add the 15, so ignore that for now. Right, here's what our queue looks like. It extends to the end of the array, but it's not filling the entire array, so we still have space. So let's go ahead and add 15, and let's modify this. Let's reduce tail modulo 10, because our array has 10 entries in it. So if our tail gets to 10, it's going to go back to 0. You could do an if statement too. If tail equals 10, tail equals 0. So now we're going to increment to 10, but it's actually going to be 0, and we're going to store our 15 at index 0. And so now, this is also part of our queue. And that's where the tail is. Sorry, let me be more careful about this. After we added the 14, our tail went to 10, which should have rolled over to 0. So then when we say add 15, we store that at location 0. We increment the tail to 1. So now our tail is right here. So the tail is where we're about to add. The head is where we're about to remove from. So this is where to add. Tail is where to remove from. Or from where to remove. If I remove another thing, right, I remove the 5 and the 6, I'd like to remove the 7. So what's the remove algorithm? Remove from the head, and then increment the head, so change the head to 3, and now our head is sitting right here. So now we've got 2 empty spots in our queue, entries 1 and 2. So our queue doesn't just start at some location in our array and extend to some other location. It can wrap around, okay, which can make your debugging interesting. Now if I add 16, store at the location given by tail, which is index 1, increment the tail. At this point, if I try to add one more thing, I have space available. I'm not using index 1. But if I add to location 1, I'm going to increment my tail down to a 3, right? And my tail and head are going to be pointing at the same location. Well, when we first started, tail and head were both equal to 0, right? That's a convenient way to know when your queue is empty. So it's a lot easier if you never allow the queue array to be completely filled. If you say that it's full when the following is true, incrementing tail would make it equal to head. So empty queue, head is 0, tail is 0. Suppose we say add 5, which puts a 5 right here, increments the tail to 1. And then we say remove, which reads from the index of the head, and then increments the head. Well, we added a 5, we removed a 5, the queue is empty again. Head and tail are not 0 anymore, but they're still equal to each other. So our is empty is just head equals tail. But because of that, we can't allow the tail and head to be equal to each other from inserting 10 things in this case. We can't insert something here and increment the head to increment the tail to be 3, which is what the head is. Yeah, exactly. So is full looks like this. If incrementing the tail would make it equal to the head, including the possibility of rolling over, because tail got bigger than the number of indices the largest index in the queue. So if tail plus 1 mod 10 is equal to the head, then the queue is full. The other way of looking at this is it's telling you that if you were to insert one more element, then when you increment the tail, it's going to be the same as head, and it's going to look like the queue is empty. Now you can get around this by setting a flag. You can have a flag saying that the queue is full, and then when you check to see if it's empty, you make sure the flag's not set and so on. But most implementations just burn one extra location in the queue and say you can't actually use all the locations at the same time, and it makes this kind of logic a little easier. But there's options on how to do that. Yeah.
So you were doing this with a linked list, and you kept this removing the like one of the pointers and then adding memory further down.
Mm-hmm.
Would it be possible that you get the last address with malloc?
Once you remove something, assuming you free it, then the next time you call malloc, you're likely to grab that block that you freed. But if you didn't free anything, if you just kept adding, that's exactly what would happen, was you'd run out of addresses, and then you've run out of memory and your queue is full. It's fun to throw some print statements into your code when you do mallocs and actually see where in memory some of these things are coming from. In your linked list code, if you print out the address that you malloc when you add a node, and you delete some nodes and you start adding more nodes, you should see those numbers getting repeated. Not always, but probably. Say again? Yeah. Mm-hmm. Yeah, which is usually just, you know, if you did a struct node star temp, it's just temp. All right, so let's think about some code. So our queue is going to be a pointer to an integer. It's going to be an array. So queue init should return a pointer to an integer. And that's really just got to do something like return malloc, however big you want your array to be. So queue add, pass it the queue, which is your array of integers, and your number that you want to add. And if you're doing this, I would actually do a define. So define your size to be 1,000 or something, and then use that in here. Because we need to know how big the array is when we're adjusting the tail and head, right? So we can roll over. So how do we do queue add? So see if the queue is full. If it is, some kind of error response, either return a value or set a flag or something. If it's not full, then queue bracket tail equals num. So save your number. And then increment the tail, reduce it modulo the size of the queue. And that's your whole add routine. So somewhere, just like with a stack pointer, you need outside of all your code, you need your head and tail. Initialize those to 0. So if I initialize my head and tail to 1, would that still work? If I initialize them to 15, as long as they're equal, doesn't matter, right? If I initialize them to 15, the first thing I add to my queue is going to be at index 15. That'll still be the first thing I remove. The next thing will go in 16 and 17 and so on. I'm moving where my queue is starting in my array, but since I roll over when I get to the bottom, I still have the same capacity in my queue. I still have the same behavior in terms of using it. So it really doesn't matter where I put those. But it's a good check for your rollover code to set them close to the end of your queue size and then force enough adds that they should roll over and make sure that works. So queue remove, you pass it your queue array, and it should return a value. So if queue empty, then there's some sort of error response. Otherwise, save your data. So your data is going to come from queue at index head, and then increment your head, reduce it modulo the size of the queue. That's your new head, and then return your data. You can do these in one step if you really want, but it makes the code kind of gobbledygookish. So queue full. Just see if tail plus 1 is equal to head. Rolling over is necessary. Queue empty. See if your tail is equal to your head. That was weird. Pretty doable. It's yeah, I thought it was my eyes. So it's a good thing to try to code up. PA3, you're actually going to use a linked list based implementation of a queue, but it's worth coding up a array based version. It's a good thing to be able to do. You'll encounter it in other courses. You'll encounter it in job interviews sometimes. And it's mainly this rolling over bit that makes it a little trickier than implementing a stack. Stacks are pretty straightforward, just increment, decrement when you push or pop. Queues, you got to manage this rollover, and you got to deal with that question where full looks like empty. So it's a good thing to practice. All right, questions? Let me talk about PA3. So PA3, stacks and queues. This is going to be a linked list based, and we'll talk about linked list queues after this, probably tomorrow. Try to stick to the concept of abstract data types, okay? Try to have a main program that uses your init function, your add, your remove, your is full, your is empty. Write a print function to print the contents of the queue and so on, push and pop for the stack. Try to implement all those functions and then just call them from your main program. And avoid having your main program do things like if head is equal to tail plus 1% 1,000, right? If you were doing this with an array, or if head arrow next equals null or things like that. Try to avoid doing that in your main program. Put those things into functions. Keep this idea of an abstract data type. So what's a queue from an abstract point of view? Initialize, add, remove. Is it full? Is it empty? Print. All right, so you're going to write a main program that's going to implement both a stack and a queue. And you interact with the stack and the queue through a simple command line interface. So you have a series of one-letter commands, S, Q, P, uppercase Q, and any legal integer. Okay, so there's two modes in which your program can operate, stack mode and queue mode. When you're in stack mode, everything that you're doing affects your stack. When you're in queue mode, everything you're doing affects your queue. Okay, and you switch into stack mode by saying S, you switch into queue mode by saying Q. Additionally, any time that you set the mode to stack mode, you should print the contents of the stack. So this is how you can look at what's in your stack. Just say S. If you want to look at the contents of your queue, just say Q. Okay, and that leaves you in stack mode or queue mode. Okay, so your main action is adding things and removing things. If you use the command P, that says remove from the top of the stack or from the head of the queue. If you type any legal integer, that's automatically asking to either push it onto the stack or insert it into the tail of the queue. So you don't have to say I space 5. You can just type a number, and it means go ahead and add this. And then uppercase Q quits the program, and you should free all your memory. So let's look at what this does. All right, so a little help statement, a little welcome message. There's how you're supposed to use the program. So I'm going to start off in stack mode, and it tells me I'm switching to stack mode, and my stack is empty. Okay, I'm going to push a 12 onto my stack. And if I do the S command, it'll tell me the top of my stack has a 12, and that's it. Got one thing in my stack. I'm going to push a 14 and a 16 and a 20. And now if I look at my stack, there's what it looks like, 20, 16, 14, 12. And I'm asking in the assignment that you always print the top of the stack on the left. You print the entries on one line with spaces in between them. Now if I say pop, what should it pop off the stack? It should pop off a 20. So I say P, and there's a 20. And if I look at the stack now, it's got a 16, 14, and 12. And if I say P again, it'll give me the 16, and again gives me the 14, and now if I look at the stack, it just has a 12. And if I pop that, and I look at my stack should be empty. And if I try to pop again, it should say stack is empty. It should not blow up, should not segfault, should not destroy anything. Don't delete my files. So stack is empty, but I can push more things in. And there's my stack. Okay, I can switch to queue mode, and my queue is empty right now. There's the head on the left, tail on the right. If I switch back to stack mode, my stack is still there. Okay, these are two independent structures inside your code. So I can switch back to stack mode. I can push a 17 on there, and I can go back to queue mode. My queue is still empty. Okay, so my queue, let's insert a 1, 2, 3, 4, 5, and look at my queue. The head has a 1, the tail has a 5. The 5 is the last thing that I put in. So it's going to be the last thing that gets removed. The first thing that's going to be removed is the 1. So I can say P for remove, and there's my 1. And if I look at my queue, now it's got 2, 3, 4, 5. And I can remove the 2 and the 3, and there's my queue. And if I add a 6 and a 7 and an 8, those go in at the tail, and they're queued up behind the 4 and the 5. If I go back to my stack is still there. I can remove the 17 by saying pop, and now my stack looks like that. I go back to my queue is still there just the way I left it when I switched to stack mode. Okay, 2 totally separate structures. Inevitably, some people try to combine these into a single structure, and it's a real nightmare. Okay, you got a stack, you got a queue, they're totally separate from each other. So I can pull things off the queue. There's my 4, 5, 6, 7. There's my 8. If I try to remove one more, it'll say queue is empty. Right, nothing in there. Put in 3 things, go back to my stack, pop those off, put in 3 things. There's my stack, there's my queue. Right, and here you can see the whole LIFO structure, right? I put my entries in 1, 2, 3. In the stack, they're in the backwards order. In the queue, the order is preserved. That's the whole essence of FIFO and LIFO, queue and stack. Make sense? Yeah. No sorting, right? Queues don't sort, stacks don't sort. The order is strictly determined by the order in which they go into the structure. So it's going to be implemented with a linked list, but some of the code's going to be very different. It's actually going to be simpler than the linked list you did for PA2, right? Because you're going to insert really close to the sentinel for a stack. All right, anything other than a legal character gives you a help message, and a big Q quits and frees your memory, except I'm not freeing my memory because I wrote this last night like at 11 o'clock, so I left that for later. All right, so we'll have to talk about this tomorrow after we talk about queue implementations with linked lists. But basically, you're going to use linked lists for the stack and for the queue. So 2 Sentinel nodes, 2 linked lists, totally independent. I won't use tests where you'll run out of memory, but you should handle trying to remove from an empty structure. If you get an underflow or remove from an empty queue, give an error message, but keep accepting commands. Don't destroy any of the structures, and so on and so forth. Test your code thoroughly, put in good comments, put in a make file to build an executable, put it in a tar file, upload to Canvas by 2 weeks from Friday. That'll be PA3. So we got to talk all about list-based implementations of queues. We'll do that tomorrow. And stack queues you've already seen. Stack lists. All right, good enough? Cool, I will see you tomorrow.